In this video, I will illustrate how to build a binary classification model using keras TensorFlow. Because many who are learning this for the first time do not have the background to understand splitting the data between training and validation set, I intentionally keep the entire data set as the training set and also the data set to evaluate the model. In future lectures, I will discuss how to build a classifier on a training set and evaluate on a different validation set. But for now, let's assume that we do not split the data set and we simply want to build a binary classifier for the data set that we have at hand.
For this lecture, I will use a wine quality data set. In this data set, the task is to given certain chemical properties of a wine, we want to predict whether the wine quality is good or not. And to create this data set, I have manually set a threshold of 5.5, above which we consider the wine quality to be good and below that to be bad. But for now, that doesn't really matter. What we have at hand is a classification data set. And I will start by downloading the data set. And let me preview the first few rows. So what we have at hand is a data set with various features as input, and then the last column is our output column. Now notice that this is not a binary value, so we will convert this into binary value as we work on this. Let me start by loading the data into a NumPy array. Now let me check the number of rows and columns in the data set. So I have 1500 rows and 12 columns. So this gives me the index of all the rows which have the last column less than 5.5, and then I would like to set the last column to 0 if that is the case. Similarly, I can check for all the values that are more than or equals to 5.5 and then set them to 1. Now I would like to check the first 10 rows of this data. So the last columns have become 0 and 1, but since this is visually difficult to understand, I'm going to change the print options. Now if I go back and print the same 10 rows, we see that the now last column has become all zeros and ones. So now this problem has become a binary classification problem. Basically, we're asking, given all of these inputs, can we predict whether this wine is a good quality or a bad quality? We also want to split the data into inputs and outputs. So my input X equals give me all rows and all the columns up to the last column except for the last one. And then my Y is data set, give me all the rows, only the last column. To make sure that I have the data shape correct, number of rows and columns, I'm going to do X dot shape and print Y dot shape. So this gives me 1599 rows, 11 columns, and then 1598 rows and single column. So this will be my input and output to the machine learning model. I also want to normalize the data. Although I see that most of the numbers are between 0 and 1, some values may be off. I'm also going to normalize the data. So for that, I'm going to calculate mean equals X dot mean with X is equals 0. And I'm also going to subtract the mean from my data points. So my X is now mean subtracted. I'm also going to calculate the standard deviation. Then finally divide X by the standard deviation. Now it is extremely important to remember not to do these things more than once. If you do these more than once, then you're calculating mean of mean and all of that, and your numbers become all messed up. If you accidentally run this twice or more than once, then it's always a good idea to go back, load the data set again, and then repeat everything so you have a clean, normalized data set at your hand. So we now have all our data ready. It's all broken into input and output. We also have normalized the data, and our Y is all values with zeros and ones. So we are now ready to design our neural network to do the classification. We will start by importing the sequential and dense classes in keras library. So I'm going to start by building the model. Model equals sequential, and then we're going to add the first layer to the model, a dense layer with say 8 neurons in it, and then the input dim for this model, input dim will be equals to 11. I'm also going to actually set this dynamic. So this is calculated from my input data. So X, give me the first row and all columns. And then let's choose activation as something that's widely used and works very well. ReLU is a nonlinear activation that pretty much works well for many problems. So I'm also going to copy this line, create another layer of neurons, and this time I'm going to choose 4 neurons in this layer. This doesn't need to be there because only the first layer of neurons is supposed to receive inputs. And then after this, as a third layer, I'm going to add a sigmoid layer. So this one, last one has to be sigmoid because this is a classification problem. Also, we only need to have 1 neuron at the end because we only need to predict 1 value as the output. So our model is ready. So I will run this cell. And now something interesting that I can do is run model dot summary to see how my model looks like. So here's a summary of my model and the number of parameters involved in my model. So let's look into this in a little bit more detail to see how the model receives inputs and how it makes predictions and why the number of parameters are the way they appear here. So here's our code where we did model equals sequential. We put n equals 8 as the first number of neurons in the first layer, and then we have input dim. This is 11, and then 4 neurons in the second layer and 1 neuron in the last layer. So essentially, if I rotate my data by 90 degrees, this is how my data looks like. Here's my input numpy array X over here. These are all my input columns. And here's my output Y. This is the wine quality, right? So we have converted all these numbers to zeros and ones. Output labels Y, and this is my input. Each of these input go into these 8 neurons that we have in the first layer as input. So the first neuron receives all of these input features as inputs, except for the output. The output doesn't go into the input neuron. So these are 11 inputs to the first neuron, and plus there's a bias too. So each neuron basically has 12 parameters associated with it. So the second neuron similarly receives all the inputs from each of these input variables. So this is 12 times 8. That's why this is the 96 weights and biases total in the first layer. Now, the output from each of these 8 neurons feed into the second layer of neurons, which are 4 of them. So first all the way to 4. So each neuron here receives 8 inputs plus 1 bias, and each input receives 9. Each input has 9 weights associated with it, and then we have 4 of them. So 9 times 4 equals 36 parameters in this network here. And the final neuron in the last layer receives inputs from the 4 neurons in the previous layer. So this is the layer 1, layer 2, and layer 3 of our neural network. The entire thing, this entire thing is our neural network model now. And it has 4 weights that multiply the 4 inputs plus the bias makes it 5 parameters for the last layer. Parameters. Now, as with the previous linear regression or logistic regression models, so the model makes a prediction, and after the prediction is made, error is calculated using the true labels, and then the signals are sent back to the weights in the neural network to update the weights so that it can make a better prediction each time. Now, ReLU or rectified linear unit is a very commonly used activation function or nonlinear activation function. So as soon as these inputs are multiplied and summed, so ReLU is applied here in each of these activation. So we need sigmoid in the last layer because if we are building a model to do binary classification, that is to predict a score between 0 to 1, then we always have to use sigmoid as the last layer's activation. Now coming back to our model summary, this is how we have 96 parameters in the first layer, 36 parameters in the second layer, and 5 parameters in the last layer. Total, there are 137 parameters in the model that the model has to learn. So the next thing we do is compile the model. We will use loss as the binary cross entropy. That's the standard loss for classification problems. We use a standard optimizer, and then we choose metrics as accuracy. Next, we call model.fit to actually do the training. So I'm going to set x as my input variable x and y as my output variable y. Let me choose epochs equals something like 256, and then set verbose equals 1. So here, let me do the training. I see that the loss is going down, which is a good sign. That means that the training is working. It's going even further down, 0.45 and 0.44. So I could further train this to get even lower loss, but let's continue now. Now with this model at hand, now I can do prediction equals model dot predict, and then supply my x as input, and then I can do print prediction. Let me print the first few outputs, prediction 5. This gives me the probability for the first few data points. Now to see how these predictions are, I can also print the true labels. So I can do print my y, give me the first 5 values. So for the first 5 values, for the first 3 were all predicted to be have a very low confidence, predicted as poor quality wine, and they are indeed poor quality wine. The third one was predicted to be almost a good quality, more than 0.5, and it is actually indeed a high quality wine. So the predictions make sense. It's making reasonable good predictions. Now, in addition to quickly checking how our predictions look like, we can also quantitatively and in a way thoroughly evaluate our predictions. And to do this, we're going to make use of the scikit-learn library. So I'm going to import accuracy score, precision score, recall score, and F1 score from the scikit-learn metrics package. With these libraries imported, I can calculate accuracy between my true values, y, and predictions using the following. I can simply do my accuracy equals accuracy score, and then true versus prediction. We also need to round our prediction so that our predictions actually become 0 or 1. If it is less than 0.5, it becomes a 0. If it is more than 0.5, it becomes a 1. So this gives us the accuracy of our predictions. I can print my accuracy to see what my accuracy is. So I see that it's currently 78.9%. Now, before I start thinking whether or not this is a good prediction, there's something very important that we have to think. Although this looks like this is almost an 80% accurate prediction, something that's very important to keep in mind is what is the baseline. So in our case, what we have is if I do length y, I have 1599 rows. And then now the next question I would like to ask is how many of all the values in y are positive? For that, I can simply do y.sum and see what that number is, 855. So in other words, what I have is 855 divided by 1599 is 53%. So around 53% of my classes or wine qualities are positive. So 0.53, this percentage are good wines. So this percentage that we got are good wines, and the rest are bad wines. Now, when evaluating a binary classifier, something that we have to be very, very careful about is to obtain something known as a baseline accuracy. What this means is, say for example, our model is very smart and it always predicts everything as a good quality. That is, everything as a 1 instead of a 0. So it does never predicts, does not, the model does not predict 0. So if our model did that, then it would always get the positive ones right. That is, its accuracy would be 53% minimum, because it knows that if it predicts everything to be in the class 1, then it'll get the 53.4%. The problem becomes even more important when your data is much more imbalanced. Say, for example, here I only had 100 out of 1599 data as positive. In that case, if my model always learned to predict everything as negative, eventually getting 1499 of them correct, my accuracy would look very, very high. But that high accuracy is only because my model learns to make the bigger class prediction correctly. In other words, what we want to see is this percentage that we get, that is the ratio of larger set among the positive or negative set divided by the total data points is your baseline accuracy. Your model's accuracy must be higher than that. Now, in addition to accuracy, we can also calculate other things. I can calculate precision using precision equals precision score of my Y and predictions. So if I print precision, this gives me how precise my model is. And similarly, I can calculate the recall score and F1 score. These four metrics that we saw, accuracy, precision, recall, and F1 score, are the standard metrics to evaluate how good a binary classifier is. You can read more about them and how they work, but these are standard metrics. No matter what problem you solve for binary classification problems, these are the standard metrics. It's always a good idea to use more than one metric to evaluate your model.